Okay, it's 11 o'clock. So let me welcome you to our next session of capstone presentations for students wrapping up in the spring 2 term. I'm Jim Detweiler, the faculty lead for the Geospatial Programming Certificate, for those who don't know me. We have, it looks like, 5 presentations lined up for today. Quick few reminders. Presenters, you're going to have 15 minutes to give your talk, followed by 5 minutes of questions. I think I caused some heart palpitations the other day when I said 25 minutes, but it's 15. If you have a question for a presenter, please enter it into the chat box. You might also consider typing your question up into a separate text editor and copying and pasting it into the chat box when the presenter wraps up so that you don't distract them during their talk. Presenters, when you get a question, please read it out loud so that anybody watching the recording will know what you're responding to. And also presenters, please put your email address into the chat box in case anyone would like to follow up with you. All right, so first up, we have Rob Ford, who is going to talk to us about placing fire trucks and why and how. Rob, are you ready?
I'm ready. It says host disabled participant screen sharing.
Okay, let me see if I can, there we go. You should be able to, okay.
There we go. Everybody able to see that?
Yep, looks good. And I can hear you just fine.
All right. So my name is Robert Ford, and my master's capstone is basically trying to figure out where fire trucks should be placed and why should we place them there. So a little background, I'm a GIS analyst for the Columbus Division of Fire, and we respond to about 160,000 emergencies a year alone. And we're always trying to evaluate our current business model, where fire stations are at, where they might be needed, if our vehicles are in the right location. And so originally this capstone was to look at 2 types of vehicles, rescues and ladders. Once I delved into it, I really only had time to be looking at ladders, but all of the concepts that I'll present today would be the same for rescues. It would just be a different data set that these techniques would be applied to. So this map here is a map of the city of Columbus boundaries and the ACS census tracts populations. So these darker areas are areas of high populations. You can see the outskirts are more where people are living. Downtown area here is mostly businesses, which is kind of to be expected. So what's a ladder? A ladder is the largest piece of equipment that a fire department typically has. For Columbus, we equip them with the jaws of life. They have ladders, obviously, and long extensions of hoses to reach high up with these ladders. We primarily use them for fighting fires, rescuing people in high places, people that are trapped in cars, and they are very expensive, usually costing well over $1 million. And so they're very picky about where and why we should place them before they go ahead and buy them. So where are they? We have 16 ladders right now out of 35 fire stations, and together between January 2020 and 2022, they averaged 13,500 calls for service annually, roughly. This map here, these highlighted red stations are Columbus Fire ladders, and these blue ones are outside agencies that we sometimes have to call for help for ladders that we don't call for their ladders too often. But you can kind of see the downtown area has the bulk of the ladders. We also have standards of cover that we have to meet for different purposes. And our goal right now is 8 minutes or less for the first vehicle on scene. And so ladders being as large as they are, they have a hard time getting around some of these tighter neighborhoods, narrow roads, and construction. So one of the first things I did was use the ArcGIS Pro network analysis toolset to create what are called service areas, or some people call them drive time areas. And essentially it uses a street network data set, and there's speed limits, lengths, intersections, and direction of travel to basically see where things can get to within a cutoff. So this map here, I did 4 minutes in the green, 6 for the yellow, 8 for the red. And this purplish color is kind of where the gaps in coverage are. This is the corporate boundary. So you can see there's no coverage. Anything that's occurring over here for a ladder is probably going to take 8 minutes or more. And same over here on the west side and southwest side. These red areas are, again, these are theoretical. This is perfect traffic conditions. They're able to go the speed limit. And so these red areas are also areas of concern. So what are the actual travel times? I decided to use point pattern analysis with the optimized hotspot analysis tool in ArcGIS Pro, which uses the GI star statistic. So I fed into the data set all of the 911 calls that ladders have been on, and it spit out a z-score and a p-value for each of these 911 calls. And actually, I have it already open here. And so you can see these red areas are areas where travel time is clustering in the higher range. So this is kind of where our problem areas are at. These blue areas are densely clustered, low travel times, which is a good thing and makes sense around each of these stations. So you can kind of see up here in the northeast area where that gap in coverage was revealed from the service area analysis that kind of marries with that data. And the same here and here. This area, actually, if I go back to the service areas, was actually theoretically they could get there in time, but I know just from being from the area, there's traffic they have to contend with because the airport's right here. So that's not always the case. And if I actually come in here and select this area, you can see, I'll just roughly select it, but it's not really meeting our goal of 8 minutes in this area at all. And ladder 8 is the one having to come out of downtown to help out in this area, leaving a gap in coverage here when it, while it's busy over here. So the next thing that I did was called emerging hotspot analysis. And this is a form of space-time pattern analysis that ArcGIS Pro has. So I had to create what's called a space-time cube, which is a way of looking at your data through space and time and seeing how it clusters through time and space. And so it uses the same GIS star statistic as the hotspot analysis. It takes the nearest neighborhood analysis into account. So it's averaging the 30 nearest neighbors is what the Esri tool does. And so this downtown area, according to the Esri analysis, is an intensifying hotspot all around. And so it doesn't really make sense to maybe move these ladders out of here since they are seeing an increase in fire events and fire alarms and other things like that. This northeast area where there was a gap in coverage, there's not a lot of run volume happening here. This is a cold, persistent cold spot. So for the 2 years that I analyzed, it didn't really see a trend in any way over here, but it's low volume. And so while the response times aren't very good here, and it kind of behooves us to put maybe something up here, they're not going to get a ton of run volume maybe as some of these other ladders would have. Some of the other interesting areas were these, they're called new hotspots. So in the last time period that I analyzed, which was 2 months, they basically, all these runs in these areas, all the 911 calls in these areas are escalating versus all the other previous time periods I had looked at. I also decided to do what's called a vulnerability score. I had read some other papers that had done this in the past, and I essentially just ranked the ladders based on these different criteria. So I looked at how many calls they had responded to, how many times they had responded outside of their own district, their mean travel time, how far away they had to travel, because sometimes they're already out on a 911 call and they'll get dispatched from that one instead of their station. kind of an indication of how busy they are, and maybe perhaps gaps in coverage. Also, how many 911 calls they went on that needed multiple ladders, so like more serious fires, for instance. How long they were on scene for in total, on average, and also something we call turnout time. So turnout time is how long it takes for them, once they get the notification, to actually mark that they're en route to the emergency. And you can see here, it's kind of hard to see because it's so small, but they're all around 1 minute. The very, very low variance between all of these ladders. But so the top vulnerable ladder that may need help is ladder 24, followed by 12, 22, 28. So if I go back to this map, ladder 24, this ladder here, if I select it, remove this filter, you can kind of see they have a pretty large range because there's no ladder up here to the northeast. So they could totally use some help, be it another ladder or just moving into a new station or something like that. Ladder 12 is in a bad part of town. This is kind of the bad part of town for Columbus. And if I look at their calls, they have a similar large range here because there's this gap here in the southwest. So I made a map with those same hexagonal grids from the emerging hotspot analysis to see what it would look like. And it more or less mimics what we've been seeing in all these analyses. The northeast area here is, could use some help. Downtown area always could use help. And more of these outer line stations. And the final thing that I did was called location allocation, which is a form of network analysis. And it uses the same street network data to basically assign a 911 call to the closest station given the parameters. So the parameters for me where I put in all of the fire stations that we have, and I said, show me pick which stations would cover the most 911 calls in under 8 minutes. So this map here is with our current 16 ladders, and you can kind of see the distribution and run volume here is pretty scattered. Station 11 and 34, they're not taking a whole lot of responses. And it also took away these downtown ladders. As you can see, they're still remaining as candidates. They weren't chosen after the model was ran. The model basically said station 25, 3, 12, 20, they could all theoretically get to this area within 8 minutes. But as we know from the actual hotspot analysis, that's not always true given, traffic or what have you. So the administration actually has 2 new ladders that they have on purchase that they want to kind of figure out where they should go. So I put in 18 ladders, and again, it took away these downtown ladders and kind of moved them to these outer regions that we had talked about where they needed help. And again, the cover or the amount of calls that some of these stations would be going on would be kind of low. So I did, let's require the 4 downtown stations, and that kind of more or less evened it out and shows some of these stations. Every way I sliced it, it showed was station 29 should probably have a ladder. So the recommendations in the end, after presenting some of this to the administration, were these areas. Then this northeast area, they already had kind of an inkling that something was off here. When I analyzed, this is a dashboard of all the parcels. And so this area has the most commercial and residential property value. This west side here has a large train depot and lots of industrial buildup, lots of warehouses. So this kind of has a high hazard, and there's actually no fire station at all here. So that might actually be looked at for a new fire station. This area here was revealed through this optimized hotspot analysis as an area of concern that they had not considered previously, which was kind of eye-opening to them. There again, you can see between these yellow stations, there's this large gap in coverage, And it's right next to the international airport, so there's more of a hazard, not necessarily that it has a lot of parcel value or high hazards in the actual area, but there is the international airport here. So if 28s and 5s are out on a run somewhere, they might not have the coverage that we would want to see. So the future considerations, they were talking about buying a new vehicle that you see here called a Quint, which is a smaller, more nimble ladder. And essentially they would be able to take some of these lower priority runs and kind of free the ladders up in case there are large fires or something happening at the airport, like I just mentioned. And also we want to kind of look at where ladders are actually absolutely necessary to have. Some of the call types that they're being sent on are things like service runs, cardiac arrest, overdoses. That's basically if they're the last responder that can respond within a timely manner, they're chosen. So maybe look at maybe sending other vehicles on those types of runs that don't necessarily need the capability of the ladders. The last thing that we want to look at is future city growth in terms of construction, zoning, population expanse, things of that nature, because that would just help us potentially create some sort of regression model to forecast where 911 calls might be going up in the future. I know that was there was a lot to take in. I have a lot more that I could speak on for all this analyses, but I kind of chose what I thought was pertinent for our administration and for this presentation. But I'm happy to answer any questions you guys have.
All right, thanks, Rob. That was really good. Looks like you've got one in the chat box already.
Yeah. Yes. So I did for actually my advisor's previous class, the target hazard analysis. And
could you read the question quickly?
Oh, yeah, sure. It says, Dan Steiner's asking, when you created your space-time cube in ArcGIS Pro, how did your results match up with Esri's target hazard analysis? So when I did that, it actually showed the west side as being having the most hazards. So kind of this area here had Station 26's area had the most hazards, followed by, if I remember correctly, Station 6, just because there's a lot of commercial buildup in the area. And so it lined up pretty well. Blake is asking, is there any way to include traffic in a network analysis, or is it too variable / lack of data? So there are ways to incorporate traffic. It's a little bit different for fire trucks because they're allowed to go over the speed limit a little bit. It's kind of frowned upon, but that's how they make sure they get there in time, right? And we also have certain things that we allow where they're allowed to go down the wrong way on a one-way street if it gets them there very fast and it's not that big of a road. So yes, you can incorporate traffic, but I have to read up more on the literature to see how others have done that. John is asking, for ladders, does it make sense to incorporate building height into future analyses? Yes, that is actually one of the next things for us to look at, because that would behoove us to have a ladder in areas that have building height, right? Just so if there's a fire in a high rise that we can get a ladder up there to rescue people. So Fritz Kessler is asking, what were some of the challenges in using a dashboard with this data? So there is a lot of data. So this dashboard that I made, the emerging hotspot analysis, as you saw, it's a little bit sluggish. I had to really prioritize what I wanted to show here. But overall, it was phenomenal to be able to see things up, all these different stats on the left update as I select things. So. Someone is asking, what was the time window of the data you collected? Was it during any lockdown period? If yes, do you expect it to affect the results in a significant manner? So it did, it was from 2020 to 2022. And so, yes, I do expect that to affect our results. One of the challenges we've had is the administration likes to kind of test things. So they'll take certain vehicle types off of certain emergencies for a short time period and then put them back on. And that was happening a lot right before COVID kind of hit. And so that's why I didn't go back any further, because it would really skew the data because of that. But also COVID definitely has some sort of impact here because, lockdown, everybody's at home. There's not a lot of we actually saw a pretty sharp decrease in auto accidents because of that. So yes, it will definitely affect the results going forward.
Rob, I had a quick follow-up to the network analysis. You mentioned the ability to go the wrong way on a one-way street. Is that something
Yeah.
that you can account for using the network analysis tools?
Yes, so you can say whether you're allowed to go the wrong way. It's kind of hit or miss because the way our 911 system operates is, if I zoom into the downtown area here, we try not to allow them go the entire length of more than so many feet on a one-way. Like if the event, I'm not familiar with the configuration of our 911 system per se, but I know that there is so many feet that they'll allow them to go, so they don't actually go the whole way on a one-way, the opposite direction. But yeah, there is a way to account for that.
Cool, good. Any other questions for Rob? Well, great job. Columbus is lucky to have this sort of analysis going on for them. So thanks for your presentation, Rob.
Thank you.
All right. Our next speaker is Tim Dolan, and Tim is going to talk to us about building a fuzzy logic tool. Tim, are you ready?
I am here. Give me one short second.
Okay.
Can everyone see my screen?
Yep, you're all set.
Can you hear me all right?
Yes.
Perfect. All right. So hi, everyone. I'm Tim Dolan, and I'd like to welcome you to my capstone presentation, Demystifying the Fuzz, Building a Flexible Fuzzy Logic Tool. Kudos to everyone for having made it here to the finish line and to the faculty who have helped us along the way. Special thank you goes out to my advisor, Dr. Panos Giannakis, for his ongoing guidance and support over the past year and some odd months. Throughout my presentation, I'll be following the outline shown here. And to start, I'd like to recap some of the introduction and background from my proposal last year. If you tuned in before, trust me, it'll feel like it was much longer ago. As GIS professionals, we use our skills to acquire and analyze data to solve questions we ask ourselves, or ideally, someone pays us to answer. Some of these questions have cut and dry answers, but many do not, including those related to site selection. The process is complicated, and while there are definite wrong answers, there can be several correct answers, all depending on different factors. One of these factors is the ever-changing criteria we consider. These are based on data that can be updated and retrieved every month, week, or even 5 minutes. The criteria used in yesterday's analysis will likely not be relevant for the same one we plan to do tomorrow. In addition, criteria change as priorities shift within an organization or at the will of external stakeholders, not always with much notice. Once we found the best criteria, we must then incorporate the diverse preferences and opinions of our colleagues to come up with the best answer to our question. Each criterion we work with and its importance does not exist in a silo, but instead varies based on the preferences and opinions of those involved in the other criteria in our analysis. We GIS professionals are lifelong learners, but deadlines draw ever closer, and at times draft analyses need to be run before research can be completed. Leadership is looking for the core information, easily digestible with clean tables and visually pleasing maps we've worked so hard to perfect. So go ahead, rethink that legend order just one more time. Not only is there an overabundance of data, but also an overabundance of tools to explore before one is even aware of what is available for a purpose. Those newer to GIS face the daunting task of navigating both an overwhelming sea of knowledge, often contained in academic articles behind a paywall, and also learning the applications of the 200-some spatial analyst tools in Esri software alone. Personally, I face these same problems in my work as a GIS and real estate analyst in local government, but they're not particular to my job there. They've come up in my previous roles in community development and in my part-time work in the natural sciences. True, the problems I was asked to solve may not be identical to those in planning roles everywhere, but we could all benefit from a common solution. So you may have guessed the solution I proposed was a flexible fuzzy logic tool. This tool is inspired by my experiences, but its design makes it applicable to those in similar roles. Fuzzy logic isn't new, and I didn't reinvent it, but I wanted to bring its power out of academia and technical discussions to afford more everyday GIS users access to it with minimal training. The tool is configured to allow users to select the data and set parameters for their scenarios while keeping the technical processes automated in the background, all in a less daunting black box configuration. So now that I have your attention, I'll get into the details. First off, multi-criteria decision analysis is a powerful way to leverage the combination of numerous conflicting data sets with expert knowledge to reach an outcome rather than relying on intuition alone. By defining which attributes are desirable in a layer and stacking each layer on top of the next, so to speak, we have a way to define the most suitable locations in a study area based on the parameter set. So how does one define desirable attributes? Well, one way is through binary or Boolean logic, based on defined membership of either being in or out. We see this in switches that are turned on or off, laws that define minimum ages for participation, such as consuming alcohol, and boundaries that govern the rules and regulations. In most cases, it's easy to define if you're 21 or over or not, or if you're in Pennsylvania or not. Some behaviors, however, are governed more by cultural norms than rules set by arbitrary boundaries. And there are analytic processes like weighted overlay that aim to explore this gray region between black and white areas of binary logic, but that may not always do the trick on its own. Enter fuzzy logic. Esri documentation states the basic premise behind fuzzy logic is that there are inaccuracies in the attributes and geometry of spatial data. We've all encountered poorly digitized layers that may be acceptable for some uses, but not others. In which cases do or don't the blue lines on the map to the left accurately represent the hydrology on the base map? Think about the modifiable aerial unit problem. How could the aggregation of point data within different polygons lead to biases and inaccuracies in our spatial data, and how could they continue to get compounded downstream? Well, let's take this inaccurate data and assign values to two specific classes, such as 1 to 10, 11 to 20, and 21 to 30. If your measurements are all 1 unit off, will you classify objects incorrectly? And are these classes even appropriate for the analysis at hand? Finally, fuzzy logic addresses situations when boundaries between classes are not clear. Think height. Most of us can come up with measurements for when we would describe someone as short or tall, but these become more subjective when introducing classes with modifiers, like somewhat short or kind of tall, and even more so when asking someone else to do this on our behalf. Remember, binary logic uses crisp data with clearly defined classes that are values that are either part of or are not. It's clear on the left of this slide that the red star is not in a green polygon. Fuzzy logic uses, you guessed it, fuzzy data with values ranging from 0 for those that are not members to 1 for values that definitely are members included in the data set, with the maybes falling in between. Fuzzy logic and the fuzzy data within it allow us to explore and include the edge areas, especially since the boundaries may be arbitrary anyway. Turning the crisp data into the fuzzy data on the right, we see the star's possible membership in at least one of the green areas. Pretending the points are bus stops and the green area is a walk shed, could the star be just enough steps away to be close enough for consideration? Now let's add just 3 more layers. Already, it becomes difficult to determine the star's membership in any one layer and assign attributes to it. How close is the star to the green areas we saw before, or the blue or red layers now also in this analysis? This is where overlay tools allow GIS users to determine a location's possibility of being a desirable site based on its membership to our defined combination of criteria in the analysis. Finally, people of any skill level benefit from automation to save time and remove potential risks of human error. In Microsoft Excel, automation can be as simple as formulas for changing or retrieving cell values. As GIS professionals, we work with automation when using geoprocessing tools. We interact with panels that allow us to select data and set parameters, but ignore the inner workings so long as all goes according to plan. These processes are hidden in a black box that makes the complex tools more digestible. This combination of multi-criteria decision analysis, fuzzy logic, and automation brings me to my goal, objectives, and results. My overarching goal was to make fuzzy logic more accessible to GIS users outside academia, to users and organizations like my previous employer. My objectives to accomplish this goal were to develop a flexible fuzzy logic tool and then apply this tool to answer real-world questions that relate to my work and similar but often different questions colleagues of mine may also face. The flexible tool combines the pre-processing steps necessary for spatial analysis with fuzzy membership and a final overlay. Combining these processes allows users to run multiple iterations of the same analysis while reducing instances of human error along the way. This tool allows users to choose their own layers for the analysis, set membership domains and weights for each layer to incorporate the varying preferences of others involved as well. I constructed my tool for use in ArcGIS Pro, the newer standard of the ubiquitous Esri software in our field. I wanted to help organizations that have already invested in this proprietary software and the additional cost of extensions like Spatial Analyst benefit from wider application of the software available to them. My tool is written in Python, the scripting language of choice for ArcGIS Pro. Scripting a custom tool affords users much more flexibility and control than by chaining together tools and processes in Model Builder, but more on that later. And so here is the interface of my custom fuzzy logic script tool. Yes, I've since made the switch to dark mode, but this makes it pop out for you a bit more. The panel can grow to be quite long, flexibly depending on the number of layers used. So on the left is a close-up of the top where users select the layers and workspace for the analysis. On the right is a close-up of the bottom where users choose parameters for each layer and the name of the final output raster. So how does it all work? First, users select a baseline raster. This defines the geoprocessing environment settings, including snap raster, cell size, and projection to be used for all other layers, and determines the linear unit for distances that can be entered as parameters for the vector input layers. If you don't feel comfortable working with your own raster, go ahead and find one. They're out there, like this digital elevation model from Pennsylvania Spatial Data Access. Next, users select a study area boundary. This polygon serves as the analysis mask, and the final output raster will have values for cells within it. Finally, users choose a geodatabase workspace where all intermediate layers in the final output raster will be saved. From there, users select the input rasters for the analysis and their corresponding parameters. These layers can be raster or vector data. In this example, there are a slope raster, highway polylines, watershed polygons, and point locations. Parameters include the option to calculate an aspect or percent rise slope raster from an input digital elevation model, the type of fuzzy membership function for each layer, the two arguments for said membership function, and the weight of importance by which to multiply the membership raster. Once the user clicks run, the tool reprojects any study area boundary and input layers not in the same projection as the baseline raster. The tool then creates intermediate rasters. For a raster input layer, this could be calculated aspect, or here, percent rise slope raster if selected. The tool then uses the values of this calculated raster, or those in the original, as input for a fuzzy membership function, given the membership type and parameters entered. Full disclosure, all of the following maps have the same color scheme, and the black and gold here for Pittsburgh is purely coincidental. For vector input layers like highway polylines, the tool instead creates intermediate Euclidean distance rasters that have cell values as distances from the vector features in the linear units of the baseline raster. The Euclidean distance raster values are then used as input for the fuzzy membership function. The same goes for polygon input layers and point input layers. Here on the right, we preview the results of the fuzzy near function, whereas the others were all fuzzy linear. Finally, the tool multiplies each membership layer by its weight parameter, sums the weighted membership rasters together, and normalizes the values to a scale of 0 to 100 for better comparison between multiple iterations of the same analysis. In this example, the Inferno color scheme shows areas of Pittsburgh meeting our criteria as glowing with suitability. To help users along the way, I configured the tool's metadata to show information for every parameter. The information text also links directly to ArcGIS Pro Help online where appropriate. For those wishing to dig deeper, the Python code contains both comments to describe nearly every line's purpose and functions to validate layer names and change them as necessary, as well as print success, warning, and error messages to the tool's messages window. As I shared before, all intermediate layers are saved in the workspace so users can examine them and refine their parameters as needed. With the tool complete, my second objective was to use it to solve problems in real-life scenarios. To demonstrate the tool's flexibility, I chose to run scenarios in 2 cities. First up is Pittsburgh, where I live and have knowledge of the literal landscape. For my second city, I chose Fayetteville, Arkansas. It's a less populated university city, but it covers nearly the same square mileage. It's in a different region of the lower 48, and I've never been there, so I can review the results without bias. All my data is from open data portals, mostly those shown here, plus some US Census data and others. So the first scenario I had proposed is determining where to hang traps to detect the invasive, highly destructive emerald ash borer. These are the criteria, 3 layers, and parameters for the analysis. Here, we get to see how 2 of the 7 total fuzzy membership functions work. These criteria being potential tree locations and parks, near transit corridors or highways, and other freight corridors. And here are the results. As you can see, we're able to focus in on areas of each city proximate to highways and rail lines, while adding additional consideration for nearby parks, thereby reducing much of the costly legwork needed to examine the entire study area. I'd like to note that for Fayetteville, the baseline raster was in a UTM projection, so all the parameters were entered in meters. A great next step would be to take this final suitability raster and apply it in zone statistics. This would allow users to determine exact properties, block groups, or neighborhoods that score well and are worth investigating further. The second scenario I had proposed was selecting sites for an affordable housing development for the reasons shown here. This scenario was also the inspiration for this entire capstone project, as it related to the comprehensive real estate strategy I was developing at the time. These are the criteria, 7 layers, and parameters I used for the analysis. This time we get to see how 3 of the fuzzy membership functions work, 2 of which we didn't use before, as well as showcase how the tool can handle however many layers you'd like. Again, here we're looking at areas near but not in major job centers. They're accessible to transit, near but not next to schools, not in food deserts. They're on buildable topography, proximate to parks and green space, and accessible to but not right along major highways. And here are these results. Even some of the same layers in both analyses produce very different results depending on the present. Pittsburgh appears to show areas of high suitability across the city, with some of the highest scores in the East End neighborhoods where such development has already been underway. And in Fayetteville, the areas of high suitability are near the city center. As before, these suitability rasters can be used to inform which areas warrant further investigation for potential development. So what were my challenges and limitations? I had originally set out to create this tool in Model Builder to keep it readable to more novice users. However, I quickly learned that Model Builder is not great for chaining together multiple processes, but it's not as configurable, or it's great for chaining together processes, but it's not as configurable for a flexible number of inputs and parameters as a scripting tool in Python. Once I got a working Python script, I wanted to keep it easily accessible, and so I had to work within the confines of my own knowledge and how a script tool's panel and input parameter types can be configured in Pro. This is why the layers are separate from their parameters on my tool's interface. And as for next steps, following a nap, I would like to get some additional eyes on the tool to help me work out any bugs I may not have thought of or addressed. If you're interested, feel free to shoot me a note. I'll share my email here shortly. The tool's user interface panel can get long, but I like the idea of adding an optional zonal statistics component. With this, users could select, for example, a parcel layer and associate the final suitability scores with actual properties. And finally, I would like to share the tool more widely with a broader audience. Hosting it on GitHub would likely not get the tool in the hands of the target audience, a potential colleague of mine less likely to navigate code-centric hubs, but it's not entirely off the table. I'm open to ideas. Here are the references for the presentation. And if you haven't already, feel free to get your questions in And with that, I'd like to thank you for your time and allowing me to demystify the fuzz and share with you how I built a flexible fuzzy logic tool. Thanks again.
All right. Thank you, Tim. That was great. Questions for Tim?
Hi, Tim. This is Robert.
Hey.
Before I worked for the fire department, I actually worked for the Forest Service doing emerald ash borer studies. So I was kind of wondering, have you read any papers on that? There's a lot of literature on that, and I was just wondering how you selected those variables.
Yeah, so I purposely took maybe a little less academic approach to my criteria, just to showcase more that the tool works with data, not prescribing where the best locations for a particular use are. But I picked my criteria of being parks as potential ash tree locations in the city, because we don't have a really good individual tree canopy data set here, as well as knowing that the beetle can travel along freight highway rail corridors, all influenced from a summer job that I had a couple of years ago working for the State Department of Agriculture, hanging trees every 5 square miles in Somerset County, checking the traps, and then coming back. And I'll share that at the time we didn't find the beetle anywhere, but now it's everywhere.
That's great. If I'd be happy to be one of your volunteers. Columbus actually has they do a tree inventory every year, so we know where every tree is at actually in the city.
Nice. Let's definitely, yeah. Let's connect here. Here's my contact info on the slide. Like to put this to some actual use. That'd be awesome. Thanks.
Yeah, thanks.
Are you planning to try to make this accessible to ArcGIS users as a whole at some point? Ideally, that would be awesome. Once we get some more testing done, see what others don't like about it, where it's falling short. And then I think it's definitely worth striking up conversations with those in the know or those with connections to try and get this in the Esri software if possible. Was this your first time developing something like this using Python? Does it show that it was? So having taken Python courses in the MGIS program, I've done shorter scripts, but this was definitely the biggest, the most chaining of different processes together, and the most interactive sort of flexible user interface I've tackled. So definitely a big fan of the online help guides, and yeah, continuing to be a lifelong learner. And thank you.
Okay, well, being cognizant of the time, looks like we should move on. Again, excellent job, Tim. That was a pleasure to watch.
Thank you.
Next up, we've got Blake Simon, who's going to shift to talking about a web app. Blake, are you ready?
Yes. Can everyone hear me?
I can hear you, yes.
All right, I'm going to share my screen now. Let's see. And can you see? Oh, sorry. 1 second. Can you see the PowerPoint screen?
Yep, I can see it.
Okay, perfect. All right. So the title of my project is Geospatial Web App Development for the Center for Louisiana Studies Archive. And the center is based in the university in my hometown of Lafayette, Louisiana. The Center for Louisiana Studies Archive houses over 30,000 audio recordings, video recordings, and images pertaining to Louisiana culture. And when I say archive in this project, I'm referring to these resources in particular. The archive spanned 87 years and includes both professionally produced and homemade recordings, mostly in French and English. And the center's goal is to preserve Louisiana cultural resources for future generations. Researchers and professional musicians also use the archives to learn about forgotten songs. I've used it myself actually to research older songs that people don't play anymore. This is one example of a photograph in the collection featuring local musicians. Alan Lomax, who was a famous ethnomusicologist. He traveled to Louisiana in 1934, and he made field recordings of songs in French and English. And these recordings are kept at the center and at the Library of Congress, also in the archive section. So here's an example of the current public-facing user interface found on the center's website. And in this example, I searched for the term fiddle, and the text results were populated. The problem with the way the data is shown to the public now, it's not very interactive, as you can see, in its current text-only format. So through the development of geospatial components, this data that's I consider vital to the preservation of my culture, the Cajun culture in Louisiana, it's going to be interactive and viewable in a web mapping environment. So after a series of meetings with the staff at the center, a few general and specific goals were outlined. The first general goal is to develop a geospatial archive data system that makes the current archive data more interactive by integrating geospatial components into the final product. And the second general goal is for the end product to be long lasting and have little staff maintenance needed. So some specific goals that we set out. The first specific goal involved the database being exported from the university's Drupal system in an Excel format. The second goal was the creation of a data entry web application so that the staff can easily update the database. And the database I'm speaking of is going to be in the form of a hosted feature class on ArcGIS Online. Third, an archive data mapping querying web application was created to perform both simple and complex queries on the archive data, and it's going to display the results in both text and geospatial form. And finally, the last goal was the creation of a website using ArcGIS Online services. And this is going to allow the applications to be embedded in the website itself, and also possibly future story maps that the center would develop. So ArcGIS was chosen as the development software and a hosting platform because the university has a recurring GIS software subscription with Esri. This subscription comes with features to develop professional web applications, and it's hosted on ArcGIS Online environment. This project involved multiple web applications, all interacting with each other and interacting with a central database in this, which is the hosted feature class. There will be a total of 3 separate ArcGIS Online applications, and those are shown in green, the green boxes. There'll be an automatic backup of the hosted feature class that has been developed. And this project, I think, was a good fit for my capstone because I wanted to attempt multiple web app development. And I was also able to pursue my interest in Python by writing backup automation and data cleanup scripts. So first, I'm going to review phase 1 of the data flow process. And the data that was originally exported was in a MySQL database inside Drupal, and the webmaster exported it in an Excel format. And there are 8,847 rows and 25 fields in the export. I performed data cleaning on the exported data. I then geocoded the data using the spatial information. And finally, the data that was uploaded to ArcGIS Online as a hosted feature layer. 2 of these steps definitely proved more difficult than I originally expected. And those were the data cleaning and the geocoding of the data. I'll start with the data cleaning aspect. There were many issues involving the original database that produced the need to clean the data. The exported data was not normalized. The coverage spatial field, which is the key field I used to geocode the data, contains multiple values for many of the field entries. You can see that one entry in the field on the right has both the city of Carencro, Louisiana and Catahoula, Louisiana listed in the same cell. In addition to this, a city and a state abbreviation are contained in the same entry. Some other issues, the date entries were formatted as strings instead of date data types. And since domains were not used to restrict database entries to correct values, multiple versions of a type of data were input. And later on down the chain, this can cause an issue in the mapping application when querying the data. The language field is a good example of this. Here you can see a section of the language field that contains 3 different ways that English and French were entered. And this was exported to me. And this could generate inaccurate results when you're trying to query French and English if you don't have everything covered, basically, to find those entries. So solutions. With almost 9,000 rows of data, total manual cleaning was not a good option. It would have taken a long time. So the solution to cleaning up the data was a combination of scripting languages and a small amount of manual data cleanup. And the languages used were Python, and more specifically, I used the pandas library for Python. And also, in the end, I used Esri's own arcade language after the data was uploaded. So pandas was used to expand the coverage spatial field and the coverage temporal field into multiple columns. So separating all that data. The spaces before characters were deleted, and fields with date data type, date data were converted to the date data type. Pandas also offers the ability to give an overview of your data. There were a large number of missing entries in many of the fields, and using pandas, I wrote a script to generate the percentage of null values for each field just to get an overview of what was missing from the entire data set. Also, the field calculator within ArcGIS Online gives you an interface to manipulate fields using Arcade. And this script fixes the multiple French and English versions by outputting a single version to a new field that I created. Arcade can also be used to extract a desired number of characters from the data, or digits. Here I'm extracting only the year from a date. So it had day, month, and year, and I just needed the date for the query that I used in the end. Geocoding of the spatial data was the second of the phase 1 components that took longer than expected. Unfortunately, several undefined errors were produced each time geocoding was attempted. So was attempted on ArcGIS Online, that is. So ArcGIS Pro was used to geocode the data, and it was successful. Now I'm going to move on to phase 2 of the data flow. So phase 2 requires the only input from the center staff within the data flow. Following the initial upload, the center keeps receiving recordings and videos that they convert to digital, and they have to have a way to append this to the original hosted feature service in ArcGIS Online. The first application that will need to be created in the archive data system is a data entry web application. One of the built-in widgets that provide data entry ability to the staff is the edit widget. And once the data is hosted on ArcGIS Online as a feature layer, that widget within a web application can append data to the previously uploaded data. And in order to keep the data app secure, the data entry app secure, the staff will need to log in using their ArcGIS Online credentials, and the web app will only be shared with the staff that perform data entry. So now I'm going to give a demo of the data entry web application. So you can see all the points populated. These are all the points in their database that had spatial information. So you can zoom in, and let's say a point here was in the wrong location. So the staff could click on the point and actually move that point to the correct location and update any fields that need to be updated. This is the edit widget. and just click update. I'm not going to do that because that'll replace some good data. They can also add new features this way. So they can place a point wherever they want and then enter any of the information in the fields that they need, and it will create that point. Okay, back to the presentation. All right. So now we're going to look at what I consider a very important topic, backup. A backup is going to protect the center from data loss, and these backups will be scheduled to run weekly, once a week. And the Python programming language actually offers the ability to automate tasks such as backup in the ArcGIS online environment. In Notebooks, actually. And Notebooks is a web-based interface provided by Esri, and you can run Python scripts in ArcGIS Online. And the final script that I created saves the current version of the hosted feature class within the center's ArcGIS Online folder. Finally, we are going to review the two public-facing applications that were created. So one of the center's primary goals is to have a web application that can search through their archive data using both simple and complex queries. The results of these queries should be displayed as points on a map and give an attribute table containing the positive query results. I also graphed the data to give an alternate visual representation. And the query widget built into Experience Builder allowed me to make this possible by selecting a data source. So I'm going to give a demo of the main public web application now. So it starts with a splash screen with their logo and a brief kind of explanation on how to use the query side of the page, and click Start Mapping. And just as an example, we can go through a few queries. So I can say I want language that's just in French and in Canada. Hit Apply, and that populates all those results. And then it also allows you to click on one of the results. This one happens to be in Quebec City, and it'll filter the attribute table to only that result. And we can see that it is in French and is country in Canada. So I'm going to clear that. And there's also a box where you can type in your search. So I'll type in Waltz and I'll hit Apply. And you can see there are 13 results here. And the last query tool that I added on here was the ability to draw a circle. So this is my current location. And let's say I want to find everything within a certain distance. And also that's in French and English. So these are the results. There are 84 total results. And also the results can be exported to CSV, and you can print it out and take it to the library where the center is, and actually they'll pull those records for you, whatever you want to listen to, or the tapes or the digital recordings. One more thing I built for them that they asked for was a way to see the data that was different than being on a map. So this kind of shows the proportion of the languages, where the countries the data is from, and mostly from the United States. And then this shows the entries by recording year. You can see they received a large amount of recordings that were recorded between 2016 and about 2019. All right, and I'm going to and one more little demo. This was something they asked for, like kind of an old school hit counter, and to see how many people actually visited their page and when they visited. So this would be just for the center staff to access. And I added this button, and all it is a link that takes you to that feature class's information page. And you can set the filter in the last 30 days. It'll tell you how many times it was viewed and the average views per day. And you can actually see it's viewed 3 times during this period, 4 times during this period. Finally, the website was created using ArcGIS Experience Builder. And within this website, there are links to the mapping application and any future story maps that the center will create. I created a link for that also. And this is a screenshot of the page itself. These are just embedded links. And some of the lessons learned, the need for extensive data cleaning was unexpected. And I think if I would have given a more intense review of the exported database data, I would have found more of the errors earlier on, instead of, as I developed the application, finding something that broke one of my functions, and it turned out to be an issue with the data itself, the original data. And then meetings with the center were vital for really establishing a solid set of needs and preventing scope creep, especially. So without these, I think it would have been much more difficult to understand what they wanted. So there was about 4 meetings throughout this process with the center themselves. And future updates, additional query parameters can be added to the web mapping application. I'm going to try to meet with the university's database administrator to see if somehow they can add domains to the current entry portal they use. That way, instead of just typing in text values and having many different types of values, only the correct values will be selectable. And also, I'll be assisting the center staff with future data uploads. I'd like to thank my advisor, Kristen Jordan, for the many web meetings and keeping me on track when I just had a bunch of random ideas, and helping me kind of put it all together and make it work. And also Professor James Detweiler for his knowledge of the credit system when geocoding using ArcGIS Online, and also access to notebooks and how to allow a user such as myself to create notebooks on someone else's ArcGIS Online environment. And finally, the staff of the University of Louisiana at Lafayette Center for Louisiana Studies. Thank you. And that is it.
All right, thank you, Blake. Questions for Blake? Nice job, by the way.
Thank you very much.
Hi, Blake. This is Robert.
Yeah, hey, Rob.
Yeah, so you mentioned you had troubles with some of the data cleanup. Did that mean like some of the handwritten stuff was kind of hard to decipher, or just things were typed in incorrectly and things like that?
Yeah, some issues actually. For one thing, a lot of the names and text was in French, and that was kind of hard to figure out a way to decipher that and make it work within a Python script. Also, they just have basically a text box for each of their entries currently, so they can type in whatever they want. So for a city name, they can type in, New York City, comma, New York, space, exclamation point, so that's what made it really hard to kind of parse that data through programming, because there were all these extra characters and spaces before. So yeah, I had to do quite a bit of manual going through the export actually, after I thought I'd cleaned everything up, and I would discover more things.
Gotcha. There was actually a tool that I'd used in my undergrad called Geolocate that Tulane University created, and
Oh, okay.
you can put in museum records like what you're talking about, and it'll like parse out, the handwritten notes that people have made to try to figure out what the lat longs might be actually.
Oh, wow. Okay. I might need to talk to you after, because there are
Yeah.
certain situations like that. And also some people, I should say, I've shown this to a few local musicians, and their question was, well, I can't listen to the recording, or I can't see the picture within the application itself. Well, that was the original plan. And then due to the number of, some of these recordings are Columbia records and some are just people's house. So there's all kind of different rules with copyright issues and photographs and videos. So that's going to be sorted out, I think, in the next year. And there'll probably be a small amount of links available online. When you click the record, it'll actually pull up an attachment of a picture or something. But right now, that's sort of not allowed, basically. Let's see, another question. Can you talk a little more about how, where this tool will be available? Will it be on the center's website? Yes, it will be a link on the main website is the University of Louisiana at Lafayette. And within that, they have a center website for Center for Louisiana Studies. And they're going to link it on the top of their page as a web mapping application. And I'm going to help them. I'm actually meeting with them in a few days to help them design the logo and things like that. But it will be available to the public from that website. And let's see there. Coding question. Okay, great. Thank you, Jeremy. Jeremy is about 2 hours east of me.
Any last questions for Blake? All right. Well, great job, Blake. That was a pleasure to watch.
Thank you.
And that's going to bring us to our next presenter. Sorry, I misplaced my list.
Me, John Coles.
It's John Coles. Thank you, John. Who's going to talk to us about a stormwater runoff calculator for somewhere in Virginia. John, take it away.
Great. And are you guys able to see my screen now?
Yes.
All right. I had some technical difficulties last time. So are you guys seeing the notes page or the?
I can see your notes page in addition to the slide.
All right. Let me see if I can figure that out real quick, if you don't mind.
Sure.
I think when you're sharing your screen, try sharing either the full desktop or one of the applications. Like if whichever one you shared, like switch to the other one when you click the share screen.
Right. So I'm hoping now you guys are the presentation. Is that
There you
correct?
go.
Thank you
Perfect.
so much. All right. So hey, I'm John. I'm John Coles. And for my capstone project, I developed a geospatial web application called the Virginia Stormwater Runoff Calculator. See, now I'm not switching pages. There we go. So to recap from my proposal, I stated that my goal for this project was to develop a web application which makes it extremely easy for the user to explore current stormwater runoff calculator values and pollution generated from an area of interest, and to understand how changing land cover values affects these values. The geographic extent for the web application is the Commonwealth of Virginia, and extremely easy to use means that the user should require no knowledge in GIS, land cover values, soil, any of that sort of thing. So also a quick refresher about stormwater. When precipitation falls to the ground, it either infiltrates into the soil or returns to the atmosphere via evaporation or transpiration, or it runs across the surface of the land to surface waters. In natural environments, whether forests or natural prairies and grasslands, almost all of the precipitation either infiltrates or evaporates into the soil. However, in urban environments, lots of impervious surfaces, things like roads, parking lots, rooftops, that sort of thing, stormwater runs across the land to surface waters, accumulating pollutants as it moves. Virginia, like most other states, or really all other states, requires certain landowners to capture their stormwater and treat it prior to releasing it to surface waters. The state of Virginia provides a spreadsheet to calculate these values. However, it's very complex and it precludes non-expert users from participating in runoff calculations. So I aim to develop an application which assumed that burden of complexity so that the user was not required to. Transitioning away from how or from why to how, my process of creating this application involved two major categories: geoprocessing and web development. So geoprocessing, in my proposal, I laid out this nice, neat plan for geoprocessing. I converted this flowchart into a Python script and thought I'll run each city and county through this app, through my script, and be done with geoprocessing in 3 days. But it didn't work. To say that geoprocessing didn't go as smoothly as I planned is a pretty serious understatement. But I regrouped. I started with raster data, so there weren't any invalid geometries. I resampled to a lower raster resolution and increased the virtual memory on my computer and broke the process into smaller steps. I calculated the runoff values for each parcel using the tabulate area tool rather than the tabulate intersection tools I had planned. I still use Python scripts, but to automate smaller, I still use Python scripts, but I broke it into smaller chunks to automate that process. And sometimes I found that it was still just quicker and easier to do the task manually. My 3-day plan ended up taking about 1.5 months, but I was still able to finish up the geoprocessing and move on to web development, which thankfully went much more smoothly. The application consists of 5 pages with 3 maps developed with standard web scripting languages. The maps were made with the ArcGIS API for JavaScript. And so without any further ado, let's just take a look at the Virginia Stormwater Runoff Calculator. Full disclosure, this next bit is pre-recorded. I have a hard time moving my mouse and my mouth at the same time.
John, do you have audio that goes with this?
Yes, I'm sorry you guys aren't hearing that. I wonder what's going on with that. I'm wondering if maybe I should just start it back over and do my best to narrate.
John, when you are sharing, you can share with the computer audio.
Okay. Thank you. Let me see if I can figure that out very quickly. I apologize for that.
That's all right. Take your time.
Thanks. Share sound. Let's see if that does it. Y'all let me know if this works now.
Well, welcome to the Virginia Stormwater
Got it.
Runoff
Yep.
Calculator.
Thank you.
The first page of the application is the landing page. The purpose of this page is to provide the user with some information about the application and to encourage them to get started. The About section opens in a modal rather than a new page and provides some background information about me, the project, and the application. In the bottom left, there is a full video tutorial which walks through the entire application to provide encouragement to anyone who is feeling a bit unsure. As noted, one of the goals of this application is to be easy to use. To begin calculating storm started. On this page, the user needs to select the city or county that their desired area of interest is located in. There are over 4 million parcels in Virginia, too many to display at once, so the selection has to be narrowed down a bit. Upon loading, the instructions for this page are open. They can be collapsed by clicking the double chevron or just by clicking the map. There are a couple of options to locate and select your city or county. The search bar, the Locate Me button, or the list of county names. One reason someone might use the search bar is if they are unsure of which city or county their area of interest is located in. For example, my home address is in Charlottesville, but I actually live in Albemarle County. Selecting the address in the search bar zooms right into my neighborhood, and I can click the map and be confident that I have selected the proper city or county. To select the clicked city or county, I make use of a hit test, which checks to determine if there are any features at the clicked point, and if so, it returns the graphic and attributes for that feature. In this case, the only 2 attributes are the city or county name, which appears in the white box for confirmation, and the portal ID for that city or county's parcel feature class, which gets passed into the browser's memory via session storage. Clicking Continue takes us to the Select a Parcel page. In this page, the portal ID for the parcel's features class is retrieved from sessions in this map. Like the previous page, there are several tools available to help find the correct parcel. In this page, I have included a base map gallery, as it may be helpful for the user to select a base map with imagery or reference points. Here again, we click the map to select the parcel we want. Click the previous page. This also uses hit test to retrieve attributes and pass them into session storage. However, this time there are over 20 attributes that are being passed to the next page. We'll click continue again to go to see the results. Here are your results. These values represent your site as it stands today. A map zooms to the parcel over a satellite imagery base map to help the user visualize the land cover values. All navigation has been disabled to prevent the user, and mostly me, from accidentally zooming or panning as they scroll down the page. In the left-hand column, you can see the various results, including the runoff coefficient and runoff volumes. Tooltips provide more information about what each of these values mean. The right-hand side provides recommendations of stormwater best management practices, which are tailored to the characteristics of each site. The final page of the application allows users to supply their own values for land cover and soil hydrology groups. This can be used to forecast stormwater runoff from planned developments or just to explore the effect that land use has on stormwater runoff. The input values are percentages, so there are a couple of checks in place to prevent a user from entering values greater than or less than 100. Clicking Continue calculates the runoff values based on the user supplied values and updates the recommended best management practices to reflect the new site characteristics. Throughout the application, various users.
All right.
Well, welcome to the Virginia Stormwater Runoff Calculator. The first page of
So can everybody hear me now that we're back to the slideshow?
Yes.
Great. So the next step involved user testing. I'm sorry, my slideshow's gotten really jumpy. I'm not sure where we are anymore. So user testing, there were two reasons to do the user testing. One reason was to detect any functionality issues or user experience issues with the application, things like programming issues, typos, areas of confusion. And then the other purpose of the user testing was to determine whether I had actually achieved my goals that I had set for this application, things like ease of use and requiring no technical expertise. And I'm really my system is really slowed down here. So test users included family and friends, coworkers, fellow students, and industry professionals. And since most of my family, friends, and coworkers live in Albemarle County, Virginia, I gave them assignments so that other cities and counties were tested as well. Feedback was received via Google Forms and email, and then I then converted feedback into action items for myself to address within the application. Here are some examples, if my slideshow catches up, of feedback that I received. This one relates to user experience and ease of use. One user noted that there was no way to close the instructions. And I learned two things from this feedback. One was that clicking the double chevron was not the most intuitive way to close the instructions. And so I added the ability to just click on the map to close them. And two was that perhaps the instructions were too long, as it does say at the very bottom how to close them. A final example of feedback I received that I thought was particularly useful was that regarding functionality, and it was that the calculate button didn't work in Google Chrome, and I had done all my testing in Firefox, so I was happy to get this feedback. And so with regards to whether or not this was a success, every user succeeded in using the application, regardless of their technical availability. And all my test users responded between 2 and 5. So we didn't have any people who rated themselves as low technical ability, but everyone still succeeded in using the application. And so I think that's a good sign. And then moving on to areas of future work. I'm so pleased with how this application turned out, but there are some areas of future work which could improve the functionality, ease of use, quality of data, and overall value of the application. One of these areas of future work is optimization for mobile and small screens. Presently, the application is designed for use on desktop and laptop computers. And it will work on a tablet, but it doesn't work very well on a smartphone. And so optimizing for mobile devices and small screens would accommodate users who do not use a laptop or desktop, and it would allow for field use of the application. Another area of future work is would be to allow the user to draw their own polygon to define their area of interest. Currently, stormwater runoff values are pre-calculated for each parcel in the state of Virginia, but there are instances where I could foresee a user wanting to work outside of the existing parcel values, perhaps a developer who's building a subdivision out of multiple existing parcels, or a large parcel where a developer is only developing a portion of the site. So allowing them to draw the polygon on the map and define their area of interest, I think would have some beneficial uses. This method would require geoprocessing to happen on the fly, slowing the application, but it would reduce the need for pre-processing. Additionally, as raw data is added by the state of Virginia, that those changes would automatically reflect in the application using this method. A final area of future work would be to vary the raster size and with parcel and or land cover density. The current design uses a 10-meter cell size statewide. In dense urban areas, such as the one shown in these images from right outside of Washington, D.C., 10 meters may overgeneralize features, resulting in inaccurate runoff calculations. However, in these rural ones shown on this next slide, if it'll show up for us, 10 meters is more than sufficient and returns accurate stormwater calculations. And so that's all I have. I really appreciate you guys sticking with me through my technical difficulties. You can find me at the email address shown on, and the link to my application is there. And I'll be happy to take any questions now.
All right, thanks, John. No worries about the technical issues. That's we all have them. You did a great job.
Thanks.
Questions for John?
Oh. So Blake asked, I know you recommended best practices based on the area and conditions. Did you have a list or hash table holding all of the options? So in my proposal, a lot of the resources I use for this application are from the Virginia Stormwater, the VRRM, which is the Virginia Runoff Reduction Method. And they do define, they suggest a number of them and kind of provide a table of which conditions might be ideal for each one. And so I kind of adapted that table into a list of kind of a decision matrix, and then I programmed that decision matrix in via JavaScript. And so it pulls all those values out of the feature class using the session storage. And it can, based on that, it determines which ones meet the site. Any others? And again, I apologize. My Zoom is running really slowly, so y'all may have typed them, but it's just moving at a snail's pace.
No worries. Other questions for John? Well, I just have a comment. I thought I really liked your application, and
Thank you.
thought it had a very nice interface, and so really nice work. Yeah, be on the lookout for making sure that you test in multiple browsers. That's
Yeah, absolutely.
It looks like you've got a link there to the tool in the
Perfect.
chat.
Thank you.
Great. Okay. Well, that's going to take us to our final presenter for this session, David Demopoulos, excuse me. David's going to talk to us about citing a long-term COVID care center in Pennsylvania's Lehigh Valley. Are you there, David?
Yeah. Hi.
Okay.
But by the way, I'm using my dad's laptop, so that's why it says James.
Okay.
Hello, I am David Demopoulos, and this presentation is a method for citing a long-term COVID care center in Lehigh Valley, PA. COVID-19, a recently discovered form of coronavirus, is a mild to moderate respiratory illness. An infectious disease, it primarily spreads through saliva/nasal discharge from coughing or sneezing. Acute COVID can have a number of symptoms, including fever, cough, breathing trouble, diarrhea, chills, pain, sore throat, and impaired smell/taste. The ongoing COVID-19 pandemic is a serious global threat. By July 15th, 2021, there were 188 million cases of the disease globally and over 4 million deaths from it. The United States alone had over 30 million cases and over 600,000 deaths by July 15th, 2021. Meanwhile, the northeastern US state of Pennsylvania had over 1 million COVID cases and over 20,000 deaths by July 15th, 2021. Within Pennsylvania, coronavirus cases peaked at 12,786 on December 10th, 2020. A secondary peak of 7,084 occurred on April 12th, 2021, and cases have been declining since then, except for a slight increase since early July. Since acute COVID is past its peak in PA, many of the people who had it could end up with long-term complications. Also, during this time, Black Pennsylvanians had over 4 times as many hospitalizations as white Pennsylvanians, while Latino Pennsylvanians had over 2 times as many as whites. Asian Pennsylvanians had slightly more hospitalizations than whites. At the same time, areas with poverty rates of more than 25% had 3 times as many hospitalizations. This evidence suggests that racial/ethnic minorities and the impoverished are statistically more susceptible to COVID in this state. The Lehigh Valley is a region in the eastern central part of Pennsylvania. Despite its small size, it is one of the most populous regions in the state. The Lehigh Valley's location north of Philadelphia and west of New York City puts it within the economic center of America. It is made up of Lehigh County to the west and Northampton County to the east, both of which contain urban, suburban, and rural areas. The region's population centers are 3 cities: Allentown, Bethlehem, and Easton. By July 15th, 2021, 75,937 COVID cases and 1,582 deaths had occurred within the Lehigh Valley. The peak for cases occurred on January 9th, 2021 at approximately 1,000. Smaller peaks also occurred, including at approximately 300 in April 2020 and approximately 600 in later March 2021. Additionally, many residents of this region have health conditions that are known to increase the risk for COVID, including air pollution, smoking habits, opioid habits, a high proportion of elderly residents, and depression among some of the elderly population. Over a third of US COVID patients have long-term symptoms. This means that over 300,000 Pennsylvanian COVID survivors are likely to have long-term COVID, and this can happen to any COVID survivor. Patients with long-term COVID, also known as long COVID and post-acute COVID, will need specialized care, and long-term COVID care centers can provide this. Long-term care centers provide medical services to those who cannot live independently. Examples include nursing homes and assisted living facilities. This project provides a method for citing long-term COVID centers, using the Lehigh Valley as an example. The criteria I used falls into 4 categories. The first, accessibility, means proximity, how close the center will be to those who most need it, including minorities, the uninsured, and the impoverished. This is important since lower accessibility is associated with poorer outcomes. The second category is distance to a larger medical center. Being closer to one increases the ease of access to services. On the other hand, spreading out the clinics gives access to more people, so both proximity to and remoteness from medical centers was measured. Additionally, the center would be sited in an area where there are more long-term COVID cases. This would maximize the center's capability and allow more people to get to the center in time. For the purposes of this project, due to sparse data, this category was approximated by risk factors. Risk factors also make up the fourth category, as those who are more likely to get long-term COVID may be more in need of post-acute COVID services. The criteria for the analysis included population density, population, remoteness, which is defined as greater than 25 kilometers from the nearest hospital, drive time to the nearest hospital, access to transportation, for which I used households without vehicles data as a proxy, income, insurance status, for which I used data on uninsured residents, race/ethnicity, female gender, as well as risk factor criteria including asthma, age, hospitalization, fatigue, dyspnea, and comorbidities. These criteria were described as relevant in the literature. The approach began with getting and preparing my data. After this, the criteria were ranked based on their relative importance using the AHP method. Each criterion was assigned points based on its ranking. The rankings were then visualized on a map, revealing which criteria are satisfied or unsatisfied within each area. Criteria that are satisfied for an area had their points added up. That way, each area has a certain number of points. The area with the most points was the most suitable candidate for the long-term COVID center site. If there would have been a tie, the tie would have been broken using the Topsis method, which is based on the ideal solutions to the criteria. In an actual scenario, after using this approach, further evaluation can occur to determine which candidate is most suitable for the care center site. US Census demographic data from MGIS was used for the age, race/ethnicity, income, insurance, and access to transportation criteria. In addition, multiple data sets were used from PASTA, a major storage location for Pennsylvania's geographic data. Census tract data from there was used for population density, municipal data from there was used for all of the criteria, road data from there was used for the drive time criterion, and hospital data from there was used for the remoteness and drive time criteria. Data for the risk factors has not been publicly available at the municipal level or below. So instead, with the aid of the literature, the demographic data was used to approximate the number of people who may be prone to these risk factors, which include asthma, age, hospitalization, fatigue, dyspnea, and comorbidities. The site with the highest suitability is located in a large section of Allentown. As can be seen in the upper right picture, the site covers much of the city, but it excludes portions of the far west and east of the city, along with multiple smaller areas. The site fulfills many of the criteria well, including all of the risk factor criteria. At the same time, it does not fulfill all criteria. For example, it is tied for the lowest site regarding the drive time criterion. The amount that the population density criterion is fulfilled varies within the site, as can be seen in the lower left picture. Darker locations fulfill the criterion better. The lower right picture shows site suitability levels in the entire Lehigh Valley. Similarly, darker locations are more suitable. Generally, but not in every case, suitability is higher in the more populous center south of the region and lower in more rural areas near its edges. The study has multiple limitations. The transparent areas on the site suitability map were either too far from roads to be included in the drive time calculations or not included in the population density data. As was previously mentioned, data was substituted for the risk factor criteria. This also occurred for access to transportation. These two limitations could have affected the results, along with the next one, the AHP process resulting in acceptable yet higher than recommended consistency ratios. Finally, the site suitability map was not given formatting such as a title and legend. For this presentation and the paper, that was not necessary, but it would be if the map was to be used in another context. This study may be evaluated using three metrics: quality, usability, and utility. Quality would be evaluated by checking the work of each step to ensure that it was completed correctly. Usability measures interpretability, while utility measures how well the project meets its goals and the audience's expectations. Each metric may be rated on a 1 to 10 scale, with 10 being highest. Notes may be added. For the quality metric, this would include where mistakes may have occurred. Part of the product of this analysis is a map of the best location in the Lehigh Valley for a long-term COVID care center, as well as a map of the scores for each area. Even more importantly, the method used for this project can apply to the site selection of long-term COVID care centers beyond just the Lehigh Valley. Long-term COVID is a serious issue, and cases are increasing. Complications from COVID will be around for a long time. Having an approach to locate care centers for this condition can bring needed aid to long-term COVID patients and help deal with the consequences of the COVID-19 pandemic. Further research on this subject can address multiple points. Limitations of the project can be addressed. Procedures can be developed for monitoring the siting process and evaluating its success. TOPSIS can be tested since it did not have to be used for this study. Whether knowing about the study area beforehand helps can be discovered, and medical research on long-term COVID can continue. The medical community will be dealing with long-term COVID for some time to come. Doing so properly with well thought out strategies would tackle the situation for everyone's benefit. Thank you.
All right. Thank you, David. Nice job.
Thanks.
Thanks, Louisa. Any questions for David? I have a question that came to mind, David. I was not familiar with the TOPSIS method. Could you maybe talk about that in a little bit more detail?
It's based on the ideal solutions to the criteria. It looks at the solutions that would be most ideal for the criteria and least ideal for them. And it kind of sorts it out so that what you're looking at is most ideal based on the specific criteria that you're looking at. There's some more specific steps to it as well, but that's kind of a general summary.
Okay, good. Thank you. I could ask another one. Do you have an audience for your work? Someone that might be able to learn from what you found and potentially put it into practice?
I'm planning to show this work to a local healthcare company in the Lehigh Valley region. They already know about this work and are interested in it, and they'll see what they can do with it once they know more about it.
That's great. That's good to hear. We have other questions for David? This often happens to the last presenter. Folks are getting hungry or getting tired. All right, well, I think we'll wrap up this session. Then I want to congratulate all of today's presenters for reaching this milestone. You all clearly worked very hard to get here and have clearly earned your degrees. I also want to encourage you guys to think about presenting your work at a conference. You know, this venue certainly makes sense in a COVID context, but as we continue to get back to normal lives, you all did really excellent work, and you should be looking to talk about it and publicize it. So with that, I want to thank everyone for coming to today's session, and wish you a good rest of your day. Take care.